Okay, welcome. Listen up. Welcome. So what we have is diffraction and polarization. So we talked at the beginning about if we take light through a single slit, we get these weird effects. And what we get is if the opening size is bigger than the wavelength, not much effect. If the opening size is of the order of the wavelength of light, we get this diffraction effect. And if we get the opening size is less than the wavelength, then we get this almost like a point source of light effect, which we've seen in the past. So diffraction gratings are kind of interesting. So turns out just a little bit of specialization here. There's two very famous types of diffraction grating. There's so-called Fraunhofer diffraction, and there's so-called Fresnel diffraction. Fresnel, no, it's French, so Fresnel diffraction. And they're both caused by pinholes in apertures and light streaming through. What the difference is either you have a lens to make this thing think like it's a long way away, or you make it a long way away. So it's geometry that makes the difference. And all I want you to know is that there are two diffraction pattern setups. One is Fraunhofer and one is Fresnel. Diffraction is the bending of light when it passes an obstacle or barrier. We can get diffraction from an abrupt edge, such as a straight edge. So this is a razor blade, and if you look at the light just above a razor blade, if you look at it, you'll see a series of lines. If you look at a bright light, if you have a gap between your fingers like I have a gap between my fingers, and if I squeeze it, I see a whole series of lines. You've got to look at bright light, you see a series of lines, and I think they're diffraction effects. I suppose on this I'd like you to know there's Fraunhofer and diffraction. I'd like you to be able to recognize that in Fraunhofer diffraction, the minimums go to 0. And in Fresnel, the minimums don't go to 0. And I suppose recognize the diagram. So just be comfortable with that. It's not the top of my list, but it's part of the possibles. Gee, I wonder what direction these fringes are at compared with my straight through direction. So I wonder what these angles are. I don't have two slits, I have one slit, but let's pretend and divide it into two. I have, let's not call it D, the separation between the slits, let's call it A, the width of the slit. From Huygens' principle, each portion of the slit acts as a source of waves. You can remember putting these little pebbles in and just seeing what happens. So light from one portion of the slit can interfere with light from another portion of the slit. We're taking Huygens and we're taking double slit, and we're kind of like merging them together. If the slit width is A, for destructive interference, m lambda equals A sine theta, looks m lambda equals d sine theta. They look identical, but this is when m is 1, we're getting a minimum. When m is 1, we're getting a constructive interference. So it's so similar and it's so different. The light intensity pattern has a distinctive shape. We're talking about Fraunhofer diffraction here because we go to a minimum. And we see there's this envelope where the first brightness is and the 0th brightness is and all that kind of stuff. So, if you look at the homework, there's probably some homework questions on this. And I think in part I have a problem with my nomenclature in that I talk about, I think, first order darkness and second order darkness. Yeah, okay. First order darkness and second order darkness. And basically, I meant first darkness and second darkness. The order's I don't want to use the term order. I tend not to ask quantitative questions about this anymore. I'll ask you about, well, if M increases, what happens to A and the like. Or if A decreases, what happens to M. So be able to pull apart this equation, but I don't tend to ask you values for theta. I leave that for interference. Okay? That makes sense? That's what I want to say. But there is some homework questions And I think there's a bit of an issue with it. Next. So we get these diffraction patterns. So what is a point source of light from one star or one headlight becomes a concentric ring pattern on our screen. And a point source of light becomes a concentric ring. If you think about it, any star is so far away that you can't see the edges of the star. So how can you see it? If you can't resolve one edge of the star to the other edge of the star, you shouldn't be able to see it. It's less than the size of one of your cells on your retina. You can't see it, and yet you see it. So what's going on? And what you're seeing is the diffraction pattern that's caused by the pupil of your eye and all that kind of stuff. And so you're seeing these diffraction blobs, concentric rings, and you can see those. So the size of the apparent size of the star is about your imaging system, not about the star. When you get to planets, you can resolve the two edges of the planet, and so you do see more of a disk. But when you see a star, you can't see the star, two edges of the star, so you see. So the star size, the apparent star size tells you about your optics. And it's all about diffraction. And that is why a narrow telescope has a lot of edge and a little bit of the middle. Diffraction effects tend to be more significant than a wide telescope. Lots of middle and a little bit of edge. So the quality of your optics goes up with the size of your aperture. Unless you're using lenses, in which case it kind of like contradicts. But they talk about diffraction limited optics. So when you buy a telescope, you look for the resolving angle. And what that resolving angle is, it says these two objects have to be this angle apart to see them as two objects. A better telescope can see things that are closer in angular terms and resolve them as two objects. A lousy imaging system needs things to be really far apart. My eyes are terrible. You know, I can't read without contact lenses because one letter merges with the next letter and I can't decipher them. All the light's going in my eye. It's just that I can't decipher them. When I first came to the States, I was going to a conference in Baltimore, and my boss wanted to drive there overnight. And I was like, I'm not driving overnight to Baltimore. So I set off the day previous, made it into a bit of a vacation, and a couple of people came with me, and the rest went with my boss. He didn't like that. He wanted us all to go together in a bus, and I didn't want to do it. So, no. And so there was a bit of a falling out. I remember trying to kind of like smooth things over when we got back. So I said, so how was the drive back, because he drove through again, Baltimore to Gainesville, straight through. Did it at night after a full day at the conference. He was like, so he said, oh, it's fine. He goes, I said, man, did you all take turns driving? He goes, well, I did most of it. I said, how did you stay awake? And he said, I just occupied myself. And then he started telling me this weirdest thing where there was this was 40 years ago, so the population of the United States was significantly less, so the roads were significantly less crowded. And he was driving, he said that from some stretches in Georgia and places like that, there was just him and maybe one other car on their side of the interstate. And he described to me how he occupied himself by, he saw a light behind him and he thought it was a motorcycle. But then as it got closer, it split into two lights and he reckoned it was a car. And he thought, oh, I just saw the resolution. So he sped up to go further in front to make it one spot again. And did the experiment a few times to make sure he wasn't fooling himself. So he's speeding and not speeding and speeding and not speeding to do this physics experiment. So So this is literally what you see. When the two objects are too close together, you will see an indistinguishable blob. When the two objects are far enough apart, you'll see what's clearly two blobs. And when they're in between, you'll see a blob with an indication of two blobs. We need a rule to decide when we've really got two blobs rather than one blob. And so we make up rules. And what we say is, when the central maximum of one image, central maximum, there's the central maximum of the red, falls on the first minimum of the other image, well, the first minimum's there, so this is beyond the first minimum. This is central maximum, that's the first minimum. It's just about there, my diagram's not so good. The images are said to be just resolved. So here, clearly not resolved. The central maximum, the first minimum, clearly not resolved. This one just about resolved. This one clearly resolved. Yep, that's the rule you use. Get the same problem in spectroscopy. You get a master charge peak for one species. You get a master charge peak for another species. You get the result. And you've got to try and interpret it. And so there's a whole bunch of science deconvolving where you try and not only recognize the fact that there's two peaks, recognize the fact that where the two peaks are, identify what the two peaks are, characterize how big the two peaks are. So a whole bunch of science. Spectroscopy, again, overlapping with this stuff. You can do the math on this. All I need you to know is this. For a circular aperture, then the minimum angle, your resolving angle, is equal to 1.22 lambda over d, where d is the diameter of your aperture. Lambda is the wavelength of the light. So your resolving angle is, so let me ask you, better telescope, bigger or smaller resolving angle? Smaller the better. With telescopes, you want a small resolving angle. So, small resolving angle, I can get a small resolving angle by making my D really big, make a big wide telescope. 8 inches, 14 inches, not 2 inches. And the other possibility is you reduce your wavelength. Reducing your wavelength means increasing your frequency. What colour has the bigger frequency, red or blue light?
Blue is like a bigger frequency.
Blue is the bigger frequency. Blue has more energy, more frequency, and will give you the better resolving. So if you want to have better semiconductors, smaller architecture, use blue light rather than red light. Go beyond there, use ultraviolet light rather than visible light. Go in the blue direction. Wavelength gets smaller, frequency gets higher, resolution effects get better.
Doesn't it like keep you up when you keep looking at blue kind of thing? No?
I have no idea. That's a biology question. Okay. So, let's take a whole bunch of diffraction, let's take a whole bunch of double slits and make it into a diffraction grating. So I get this idea like I had before where I had fringes, but they're now very intense fringes because there's so many of them. I've only not got 2 little things letting light through, I've got 1,000 little things letting light through. I get the interference effect, but I get it really brightly. And so I have the same equation, m lambda equals d sine theta. D now is, well, before it was the distance between the slits. Now it's the difference between the lines, we call it. Okay? I can use this instead of a prism. Before we had the picture of the spectrometer using a prism to break the light up into its different colours. I can use a diffraction grating to break the light up into its different colours. It works great. Don't worry about the resolving power diffraction grading. If when it was on the equation sheet it was fair game, but don't worry about that. Oh, and I need to, so this is not on, this is a typical question. So this is a typical question for diffraction grading. I have 600 lines per millimeter. That's my diffraction gratings frequency. 600 lines per millimeter means 600 gaps per millimeter. It's just, you know, the repetition distance. I have 300 nanometer light. First order brightness, second order brightness. Want to know the angle. Find angle. For second order bright. M lambda equals d sine theta. What's m? Second order brightness. 2. Just like it was with double slit. What's lambda?
300 nanometers.
We'll leave it in nanometers. As long as we're working in nanometers on the... Actually, I'm not going to leave it in nanometers. Let's just get back to units. 10 to the minus 9. What's D? Ah. 1 times 10 to the minus 3 divided by 600. If there was 1 slit per millimeter, there'd be 1 times 10 to the minus 3. If there were 2 slits per millimeter, it'd be 1 times 10 to the minus 3 divided by 2. There's 600 slits per millimeter. 1 times 10 to the minus 3 divided by 600. So this equals 1 times 10 to the minus 3 over 600 times sine theta. So sine theta is equal to 600 times 10 to the minus 9 times 600, well, that's interesting, over 1 times 10 to the minus 9. Sine theta, oh, that's not good. Have I got just some bad number? Let me just, m lambda equals d sine theta. 300 nanometers, 600 lines. I think this is too small, but let's just. Did I do? Is my math all right, go away? Is my math all right?
Your algebra's right.
Oh, that's 10 to the minus 3, isn't it? Yep. Not 10 to the minus 9, 10 to the minus 3. So this equals 36 times 10 to the minus 6, which is 36 times 10 to the 4 times 10 to the minus 6 is 36 times 10 to the minus 2. So theta is equal to sine to the minus 1 of 36 times 10 to the minus 2. Theta is equal to... Got my anybody got a calculator? I carry saying, I'm sorry. It's going to be a small angle. Let me just double check my math. Yeah, 10 to the 4. 10 to the minus 3. 21. 1 degrees? Yeah, 21.1 degrees. Okay? Okay? So what did we do? We had to know the equation. We had to know how to work out what our D was, given some kind of like methodology, you know, tell you the number of, traditionally it's the number of lines per centimetre, number of lines per millimetre, something like that. And then you got to know lambda, so you've got to be able to do math. So it's, we use this in one of our labs. You're going to do if you do the last lab, you're going to do a diffraction grating lab, in which you do this, and we actually figure out the energy levels for hydrogen using that. Using just a. The nice thing about the diffraction gratings is they're just a piece of film. You just draw lines on a piece of paper and then photograph it, and you've got diffraction grating. It's great. Yes. What?
I was not able to understand how you find
D.
Yeah, the 1 times 10 to the negative 3. How did you?
Oh, because it's a millimetre. I said per millimetre, so 1 times 10 to the minus 3. Yeah. Then divide it by 600. Yeah, cool. Okay. Last little bit. And this is. We learned when we did EM theory that we had E cross B, you know, the electric field propagates and induces the magnetic field, which propagates and induces the electric field. So we can draw them a bit like that. Yeah, we have them, you know, 2 90-degree waves. And we can say, well, a continuous stream of light would be one of these just going on forever. But light comes in photons, so we have, you know, a photon. And we can imagine drawing this inside, you know, boom, boom, boom. Yeah, whatever, yeah. If I look at the end of this, so this is the direction that light's going, I just like chop it there. So I have my B field in that direction, and I have my E field downwards. So imagine looking at the photon, and I see this like right angle. Yeah. If I have a normal light bulb, like an incandescent light bulb, or I have something like the sun, just a flame, if I was able to do this and look at all the photons, I would see one was like that, and one was like that, and one was like, got to make sure I do it the right way around. One was like that, and one was like that, and so on. They're all, it's like the football coming towards you. They're all going in the same direction, but they have different orientations of the ball, which is, you know, just the way it goes. Who cares? Back in the day, what they found was they could make some crystals. And the crystals that are really weird, and some were naturally occurring, had some really weird properties. And what you'd find is that they would not let all the photons through, certainly all the light intensity through. But what they did let through was all, well, polarized. I might as well just tell you what was going on. They found that when they made these crystals, these films, what they found was that only photons with a certain orientation got through. You lost a lot of photons, but what you got through was all polarized. And the way they'd envisaged that is they said, all right, imagine a piece of string and a skipping rope and all that, and imagine a picket fence. So you have a picket fence and you put the... Trying to get a wave that goes like that through is easy. But trying to get a wave that goes like that through is impossible. And trying to get a wave that goes like that means you get a component of it through, but not the whole thing. And that's the analogy of what they've got here. What you get is, if your polarization is 90 degrees to what it should be, you won't get through. If it's perfectly aligned, all of you will get through. If it's angularly aligned, a portion of you will get through. But everything that gets through is then polarized. All right, that's kind of cool. Does polarized light look different from normal light? I can't tell the difference. It's just photons, it's just energy. Okay, so we say we know that light is oscillation perpendicular. Light is the oscillation of perpendicular electric and magnetic transverse waves. An unpolarized light source can emit photons with any orientation. I'm just drawing the electric fields here. And you know, if you look at all they'll be all over the place. They'll be, you know, everything you can imagine will be coming out. If we put that through a polarizing filter, which has, if you like, the picket fence in that direction, we will end up with all our photons having the same direction. Some of them will be big and some of them will be small, but they'll all be lined up. We call this linearly polarized, or plane polarized, or polarized light. Okay, various terms. Why do we care about this? I want to just step to one side for a minute. We care about this because some materials are what's called optically active. What they do is they will take a wave which is like that. I'm only going to draw the E vectors. And that's coming down towards. And what they'll do is they will start twisting it. And so the light that emerges has a different polarization than what you sent in. Certain polymers will do that. Certain rocks will do that. Crystals will do that. Okay, so you're a geologist and you want to see the different phases, the different grains of the material. You can have one polarizing lens which gives you polarized light. That's called a polarizer. You then have your optically active material, and the different grains on this optically active material behave as they wish, causing twisting to the right, twisting to the left, no twisting, whatever. And you then have so now you got light coming out, which has been messed with, and now you have the analyzer. And when the light that comes out is aligned with the analyzer, you get brightness. And when the light that comes out is 90 degrees to the analyzer, you get total darkness. And when it's a bit in between, it's a bit in between. And so you get this material which looks just transparent. When you look at it through this polarizer-analyzer combination, you get this array of colors, and you can tell different grains that are orientated in the same direction and the like. That's just incredibly useful. I think it's called Zemansky imaging on a microscope. The other thing you can do, which is kind of fascinating, is certain polymers have an optical activity which depends upon, or is at least changed by, the amount of stress they are under. So I can take a beam and I can squish it in certain places, and I will see, when I get through the analyzer, I will see an image of the beam, and it will show me where all the stresses and the strains are. So I can then analyze what's going on in terms of the stress and the strain inside the material, visually. So really, really useful. For example, if you have when I was a first student, the first calculator I ever saw was in 1976. It was the first electronic calculator I ever saw. It was a 4-function calculator. It had LEDs as the display. It was yay big, bit like a 83. It cost only one guy in my entire kitchen had one. He was kind of like the well-to-do family. It cost, I suspect, hundreds of pounds, and it would do addition, subtraction, multiplication, division. I don't even think it had powers on it. I think it was like, and we all sat there playing with it and making up words. You can turn the thing backwards and it says, because we all used calculators. We all used slide rules. If you have a LED, if you have a liquid crystal display, the next big, apart from the price falling through the floor, the next big thing was the LED. It was the liquid crystal display. Liquid crystal, it's a liquid crystal, and you use various polarizing filters, and depending upon the polarizing filter at the front and whether the liquid crystal is energized or not, it acts as optically active, and so you get darkness versus reflected light. So very, very useful for that. So this idea about crossing filters is really valuable. So let's just look at crossing filters. So let's take unpolarized light, and let's have a certain filter. We'll call it the polarizer. We'll have the second filter called the analyzer. We're not going to put anything in between. We're just going to look and see what happens. And what we see is when the two polarizing filters are aligned, when the two filters are aligned, then we get light through. When the two are 90 degrees to each other, we get opacity, which is completely opaque. And when there's an angle between them, we get a bit of light through. And so Malus, never say his name, Malus looked at the relationship between the light that you get through here and the light that you put in there. And what he found was that it depended on the maximum light that you put through, the intensity, multiplied by the cosine squared of the angle between the two filters. And that would have been the last lab if we had time for it, but we don't have time for it. I can show you, if you're interested, I can show you, but it's a bit of a simple lab, so I'd sooner do the thing on spectroscopy. So we say, consider unpolarized light that is transmitted through two polarizing filters. The intensity of the transmitted beam varies as the square of its magnitude. The intensity of polarized beam transmitted through the analyzer varies according to Malus's law. So know Malus's law and know how to do it. Last little bit. I like to have polarizing sunglasses. They cost more than a normal pair of sunglasses, but they work much better. They don't seem to make the dark bits so dark, but they do seem to sort out the bright bits. They're kind of amazing, really. They're much more comfortable, I think. When I first came to the States, on vacation, I had a pair of very light blue sunglasses. I was in New York City, and my buddy I was visiting, kind of after about 3 days, grabbed these things off me and looked through them, and he said, "This is cheating. They make everything look really nice and clean." And because it was a light blue filter, wasn't polarized, light blue filter, it just favored the blue colors as opposed to the drab brown colors. And so it really affects your I mean, try. If you've not tried it, just go and try different colored sunglasses, and it makes a big difference to how you feel, I always feel tired with brown filters. I always feel tired. I use them. I get them. They're more popular. You can find them more often, but, sometimes a green is, you go outside and the garden looks great, But they're not polarizing filters. They're just light filters. When I came back to the States, I really was concerned about the sunshine, so I bought myself the darkest pair of sunglasses I could find. And they were great until you started driving and you went through tunnels and the like, under dark trees, and you can't see a thing. It's like, they're clearly not good. You look back at these old Hollywood movies and the people have dark sunglasses. You can't see their eyes at all because they're just using very dark lenses. Be nice if I could make the bright bits less bright but leave the dark bits alone. And you can. And you can by this very interesting effect. I can polarize light by using a polarizing filter. But I can also polarize light by simply having it reflect off of a reflective surface. Now, not everything that reflects is polarized. What we say is when unpolarized light is instant on a reflecting surface, the reflection and refracted beams are partially polarized. The reflected beam is completely polarized when the angle of incidence equals the polarizing angle, where n is equal to tan of the polarizing angle. And this is called Brewster's law. Again, I don't need you to know this. When it was like no equation sheet, I'd gladly have you know it. But I don't need you to know that equation. Know it to the extent that if I give you it and say what's going on, you can tell me. That's the thing. So what that means is that I can take sunlight and reflect it off water or the chrome on a car or something, and the light that comes off is polarized, and I can then use a 90-degree polarizing lens to cut out the brightness. The glare from the water, the glare from the chrome is completely polarized because of the angle that the sun bounced off it. It's all polarized. So sacrifice that light. But don't sacrifice the light from over there or the light from over there. That's just unpolarized. Some of it your lenses will cut out. Some of it will be cut out. But it's not all polarized. It's just the glare that's polarized. So you go to the pond and you put polarizing sunglasses on and you can see the fishes. And the reason you couldn't see them before is because the glare made your pupils close, so you couldn't see the darkness of the water. But, get rid of that glare and you can see the fishes. Not magic, it's just getting rid of it. Go out into a parking lot and there's cars with glare off them. Goes away with polarized lenses. It's that glare which gives you the headache. So polarized lenses don't make the darks darker, but they make the glare go away. When were polarizing lenses kind of developed? Was it last century or was it this century?
Are you asking?
Yeah. So I think it was about Second World War, actually. I think it's been around for a fair while. When did the polarized films get developed? I think it was Second World War. It might be NASA, but I think it was Second World War. Okay, so there we have it.